Welcome to massive open online course on chemical process intensification. We are discussing the topics on module 5 as optimization for process intensification, and in this lecture under this module 5 we will discuss something about applications of optimization algorithm. We have already discussed some techniques, methodology of that algorithms, and also what are the different types of algorithms are actually present for analysis of chemical process based on this intensification of the process. And in this case, we will then discuss about that how that optimization algorithms can be applied. So, we will discuss two portions of this lecture. Here applications of evolutionary optimization algorithm that is applied for chemical engineering processes, and also one example like that optimization of reactive distillation process with certain specified that optimization algorithm, like it is called simulated annealing. So, let us go back some extent of that optimization algorithms, where we have discussed the different types of algorithms for optimization of single or multi objective nature of that chemical engineering process. So, in that case, evolutionary optimization algorithm is one of the important algorithm by which you can apply or you can analyze that multi objective nature chemical processes with different constraints. And in this case, that traditional design of chemical process that will considers a set of sequences unit operations, where each equipment is generally developed to perform just one type of modification to the process stream, and that modification actually generate changes in composition, energy content, or that amount of you can say that movement of the that phases there. And so, that is why we can say that that chemical processes which will have a multi objective nature along with different constraints can be that evaluated by the evolutionary optimization algorithm. And this evolutionary optimization algorithm in traditional chemical engineering processes, you will see the optimal design problems is very complex, highly nonlinear with several constraints. So, that is why evolutionary algorithms are generally successfully used for the single and multi objective optimization of those traditional chemical processes in the area as of process design, process control, and also reaction systems, parallelly separation also you can say there. So, that is why we are just going to discuss something about that application of that evolutionary optimization algorithm. And in this case, the objectives can be decreased by intensify the process, and the new intensified process units, it should be considered in such a way that that it must have optimal designs in order to take advantages of all benefits of the process. Now, why that design of these new intensified units is more complex whenever we are talking about that chemical engineering process intensification. Of course, any process intensification we are talking that maybe that unit operations to be designed in such way that will be more complex in some extent. So, why the design of those new intensified units would be more complex? In that case, there are smaller physical spaces sometimes required in your process intensification. In that case, sometimes operating conditions to be reduced due to the existence of physical and reactive equilibria, or the incorporation of the technologies which are going to adapt for this process intensification, like microwave techniques, ultrasound techniques, to analyze or to design all those special technologies for the chemical process. It is very difficult to analyze based on the particular optimization techniques. So, because there are various operating conditions to be considered for that, and to be very complex. Therefore, the modeling of those processes is more complex than the modeling of traditional chemical processes. For those cases, you will see the optimization strategies, especially the evolutionary algorithms, become an important tool to reach the optimal design of intensified process, since the complete models of the process are not required in this case of evolutionary that optimization algorithm. So, this the optimization strategies, especially the evolutionary algorithm, that is why are very important to apply for such complex systems to get the optimal design of intensified processes. Some applications of multi-objective evolutionary algorithms are given here. You will see of course, any process intensified phenomena has different objectives whenever it will be that executing any particular process synthesis there. So, in that case you have to solve those multi-objective that operating conditions by those that evolutionary algorithms. So, what are those some special applications where you can apply the evolutionary algorithms based on that multi objective functions. Now, application like catalytic membrane reactor for the production of methanol and hydrogen. In this case, the elitist non dominated sorting genetic algorithm along with a non isothermal model can be actually considered to analyze the optimal solution of this particular process. So, we have already discussed that different type of genetic algorithms and what are the different steps and also sub algorithms, all those sets that already we have discussed in our previous lecture. So, in that case this genetic algorithm, that is non dominated sorting genetic algorithm, it is called NSGA, can be applied for such application of catalytic membrane reactor for the production of methanol and hydrogen. Another application like the use of reactive distillation where both conventional and thermally coupled systems are being used for the production of biodiesel. So, in that case again that multi objective genetic algorithm with handling constraints in order to generate the Pareto front, that is set of optimal solutions that can be applied for the analysis of this reactive distillation. Another important application there it is called transesterification reaction there in reactive distillation column. In that case optimization of that transesterification reaction in distillation reactive distillation column with thermally coupling system to be done, and for that optimization the elitist non dominated sorting again genetic algorithm can be used along with HYSYS process simulator software there. And also in the case of distillation with reactor for hydrodesulfurization process of diesel, there you can use some competitive results between total annual cost, carbon dioxide emissions and amount of sulfur compounds of the hydrodesulfurization process to be considered for the analysis of optimal solution, this distillation process with reactor for this beneficiation of the diesel by hydrodesulfurization. Another important application, it is called extractive thermally coupled sequences for the separation of ethane and carbon dioxide. In this case, you will see that the sequences can be simultaneously optimized by minimizing the total annual cost and maximizing the acid gas removal there. So, in this case, very important that what are the sequences that you are going to consider there in that particular extractive thermally coupled sequences for the separation of ethane and carbon dioxide mixture, that should be optimized by the minimizing the total annual cost and maximizing the acid gas which is to be removed. Hybrid distillation or melt crystallization, that using thermally coupled distillation schemes can also be analyzed for the optimization process, where the design and optimization can be carried out using as a design tool a multi-objective genetic algorithm with restrictions that will be coupled with the process simulator like Aspen Plus. So, these are the applications. Another applications like performing the biodiesel production in a counter current reactive extraction column. In that case, you can use the Aspen custom modular, which will actually include the multi-objective optimization of the hybrid separation using evolutionary algorithms. And for the case of hybrid separations combining nanofiltration and distillation for the wide boiling mixtures, the optimization can be analyzed under uncertainty using multi-objective evolutionary algorithms for the design of this intensified separation, that alternative can be performed there. And also optimization of the biodiesel process like production of considering in that case production that consider the raw material as a soybean oil. In that case you can do that optimization by stochastic tool with Super Pro Designer tool, and that is useful to optimize the three objective of these type of problems like maximize the net profit, maximize the number of chemical operators, and also minimize the volatile organic compounds that emitted during that production process. So, you can optimize that biodiesel process based on the raw materials of that soybean oil by this stochastic tool of Super Pro Designer based on the objectives like maximization of the net profit, minimization of the volatile organic compounds emission, and also maximization of the number of chemical operators. Now, what are the different types of that stochastic methods for optimization are generally being used, that already we have discussed in our earlier lecture, that different types of optimization algorithms, optimization methods are available to analyze or to solve the single and multi-objective optimization problems in process intensification. So, here again we can have a list here like simulated annealing algorithm based method, genetic algorithms based method, differential evolution based method, particle swarm optimization based method, harmony search based method, and colony based optimization method, and other different types of methods which are being suggested by different investigators nowadays. Even refinement of those algorithms, even new algorithms are nowadays coming, that is revealed by different investigators after their research. So, these are a few that stochastic method which have already been discussed in the earlier lecture in details. What are the different advantage, disadvantage, pros and cons, and even that how to apply those things already we have in our previous lectures. So, here we will actually concentrate on one that optimization method, it is called simulated annealing algorithm based method. Like if we consider the optimization of reactive distillation column, in that case if we take that integration approach to the simulation or optimization of the reactive distillation column by adapting the mixer or also mixed integer nonlinear programming column model that is suggested by Sirik and Gu in 1994. So, this model actually it is called MINLP, that is called mixed integer nonlinear programming column model, and these models will be discussed here for this optimization of reactive distillation column. In this case, they have actually considered this synthesis of a reactive distillation column for the production of ethylene glycol. So, they have taken some basis for this simulation, and the simulation model is based on an extension of conventional distillation columns, and the optimization is analyzed based on that result obtained by simulated annealing based MINLP algorithm. And this is also called as that SIMS algorithm proposed by that Cardoso et al. In 2000s there. So, here we can say that if the simulated annealing based algorithm, it is called SIMSA, that is called that MINLP, and which will be based on that simulated annealing. So, this algorithm it is named as MSIMSA algorithm, that is proposed by Cardoso et al. And based on this SIMSA algorithm, we can say that this simulated annealing is a well established technique for the optimization of combinatorial problems, and also this can be done for the large scale functions that may assume several discrete configurations there, as per Metropolis et al. Which is suggested in 1953. And this simulated annealing based algorithm is suitable for the optimization of mixed integer nonlinear programming problems. Like that if you are considering that synthesis of non-equilibrium reactive distillation column, there you can apply this simulated annealing based algorithm. And from an optimization point of view, this simulated annealing explores the key features of the physical annealing process of generating transitions to higher energy states, and also it can be applied to the new states on that whether it will be accepted or rejected probability criterion on that particular acceptance and rejections, which should necessarily become more and more stringent with the progress of the optimization. Now, these algorithms may be viewed as a randomization device, and it allows some wrong way movements during the course of optimization. In that case, you have to look at the picture where this wrong way movements during the course of the optimization, whether it goes through an adaptive acceptance of or rejection criteria or not. So, that is actually observed by Swayam in 1991, this type of phenomena. What are the solver that you can use that for the optimization of that particular problem of this reactive distillation column? In this case, this SIMSA solver that is suggested by Cardoso et al. In 1996 can be used, and it is a that solver simulated annealing based algorithm that was developed for the solving constraints for nonlinear programming problems. And it is generally built on a scheme that is proposed by Presh and Tchaikovsky in 1991 for unconstrained continuous optimization, and it combines the simplex method of suggested by that Nelder and Mead in 1965 with simulated annealing. And in this case, the role of that nonlinear simplex will be to generate the continuous system configurations. Also, while the role of simulated annealing is to be there to allow for wrong way movements, simultaneously providing convergence to the global optimum solution. And then this algorithm shows good robustness, like good insensitivity to the starting point and reliability, and also you can say that how you can rely on this particular system that can attain the global optimum for a number of difficult NLP problems that is reported by Cardoso et al. 1996. It may also be used with a faster non-equilibrium variant of simulated annealing program like this, that which has good insensitivity to the starting point and also has a reliability in the attaining the global optimum solution. Now, M-Simse algorithm was developed by that Cardoso et al. 1997. It is coming actually based on that extension of the Simse solver to deal with that mixed integer nonlinear programming problems. And in that case, the continuous nonlinear solver is to be used to that update the continuous parameters, while the Metropolis algorithm is used in an outer loop to update the complete set of decision variables. So, the stochastically generating scheme proposed by Dolan et al. Can be employed each time a different set of discrete variable which will be required for this algorithm to analyze. And now, this M-Simse algorithm is simple to use, since it neither requires the preliminary the identification of integer candidates for the global optimum, nor the identification of feasible or good starting points there. So, in that case, this M-Simse algorithm is applicable not only to the that mixed integer nonlinear programming problems, but also to the nonlinear programming and combinatorial problems also. When if you are applying to these NLP problems, that is nonlinear programming problems, it may perform as the Simse algorithm that is suggested by Cardoso et al. 1996, and when applied to the combinatorial problems, it performs as the original Metropolis algorithm there. That is also that given by Cardoso et al. 1994. Now, let us have this synthesis of a reactive distillation column for the production of ethylene glycol, that is described by Cardoso et al. In 2000s in their paper published in Chemical Engineering Science volume 55. So, they have given this problem definition like a set of chemical species, if you are represented by I, that will be equal to 1, 2 like this I, and also a set of desired products and production rate also, and a set of chemical reactions denoted by J like 1, 2 dot dot R. The stoichiometric coefficients for all species is denoted by nu I j, and rate expressions are given as that R j, that will be a function of that component fractions, or you can say that compositions, and also temperature, and the enthalpy of vaporization and vapor liquid equilibrium data, the feed streams composition, the cost parameters. So, these are the problem definitions which are actually summarized like this, and they have considered this that multi-trade distillation column there, and their goal was to determine the optimal number of trays here, hold up per tray. Hold up means what will be the volume fraction of that particular phases per tray, reflux ratio, condenser and reboiler duties, and also what should be the feed tray locations that are to be optimized. That was their that goal. So, it is shown in figure like this, that process ethanol water mixture there, and it will be supplied at that different tray, and what should be the optimal location of that feed tray, and what should be the optimal reflux ratio, condenser and revolving duties. So, I am not actually expressing how these operations, everybody knows that how distillation column is being operated, from the top, that what is the vapor is coming after distillation, some reflux will be sent back, and then it will be going downward, and from the bottom also heavy product will be boiled, and then it will be supplied to that from the bottom, then it will be go up like this. This the distillation, this conventional distillation column operation there. Now, in this case, the main goal is to actually determine that optimum value of that number of trays, hold up per tray, reflux ratio, condenser and reboiler duties, and also what should be the feed tray locations like this. Now, what are the reactions actually being taken place here, this particular that reactive distillation column. So, in this case ethylene glycol is produced from the reaction of ethylene oxide and water there. So, ethylene oxide plus water, that will be equal to like this, this equation is given to you here, and the ethylene glycol produced can further react with ethylene oxide to produce the unwanted byproduct, that is diethylene glycol, and in this case both reactions are highly exothermic and occur at moderate temperatures, that will allow that production via reactive distillation column. So, here in these slides the reactions are given, how this ethylene glycol is produced from that reaction of ethylene oxide and water, and also that ethylene glycol produced can further react with that ethylene oxide, that will give you that unwanted byproduct is called diethylene glycol. Now, these both reactions of course will be exothermic, and it will of course be carried out with a moderate temperature, and in that case it will allow you the production via reactive distillation column. Now, why actually this production of ethylene glycol via this reactive distillation? In this case the large difference in volatiles between ethylene oxide and ethylene glycol, that may lead to a rapid separation of these two components in the column, that may improve the overall selectivity there, and part of the heat required for the separation, that can be obtained from the heat of reaction, since it is exothermic reaction which allows the reaction, and also it may reduce the energy cost there. So, that is why reactive distillation is being actually chosen for the production of ethylene glycol via reactive distillation. And what are the data required for the problem here to optimize this process? In this case reaction data is required, vapor liquid equilibrium constants, ideal vapor liquid equilibrium data is required, what is the cost data, and also what are the different thermodynamic data, non ideal vapor liquid equilibrium data, those are actually required for analyzing this problem. And these also very important to know that here the enthalpy of vaporization of mixture is assumed to be constant all over the column with the value of 14 to 10 to the power 3 joule per mole as per CIRIC that is given in 1995. So, you may get this all data from this the paper that is published by Cardoso et al. In 2000s in Chemical Engineering Science journal. So, you can take those data for further analysis there. Now, how to actually formulate that mathematical problem for those objective function and also cost terms there. So, as per CIRIC and GU 1994, that objective function and the cost terms can be defined like this here. this FOBJ, that means here function objective function is equal to minimize of this, what are these here summation of components wise here Ci and summation of what is that Fik plus CHQB plus CWQC plus AF into CS plus CI plus CR plus CC. So, as per this equation number 1, you can actually optimize this process, where some notations are given here as per equation 1, that Ci will be equal to the cost of raw material I, Fik this is defined for the feed rate of material for I to tray K, and Ch is actually the cost of the steam and Cw is the cost of cooling water which is required for that distillation, and also that Qb and Qc, that will be reboiler and condenser duties which are very useful for that distillation operation. Af is actually referred to an annualizing factor, and also CCS, CCI, CR and CC, all those terms are actually referred for the installed costs of the column shell, trays, reboiler and condenser respectively. So, here in these slides those terms are given here, and then how to calculate the column investment cost that can be obtained from this equation number 2 and 3 are given in the slides here. It is given by Douglas in 1988, and this CS can be calculated from this equation number 2 and CCI can be calculated from this equation number 3, where the terms are defined here. M and S actually represented here for the Marshall and Swift index that is published periodically by the Chemical Engineering Journal, and D is the column diameter, H is the height of the column, and FC and FC dashed are construction factors, and also HK is referred to as the height of the tray K. So, from these two equations you can calculate the column investment cost as per this equation. And then how to calculate the reboiler and condenser investment cost, that can be actually calculated by these two equations of 4 and 5, that is Cr, that is cost of reboiler, that will be equal to Cr1 plus Cr2 into Qb, and Cc for condenser investment cost, that will be Cc1 plus Cc2 into Qc, and here the height of the tower is evaluated by H, that will be equals to H0 plus summation of Hk. If there are n number of trays, then you have to calculate that height respectively, where here H0 is a fixed extra column height to be considered, which will corresponds to the free space below the bottom tray and the above the top tray there. And here the heights of the liquid in tray K, that will be denoted by Hk, that are calculated by Hk, that will be equal to H mean plus 1.27 into Wk by here d square as per equation number 7. And in this case in the slides this Hk to be calculated based on that minimum tray spacing, and also what should be the corresponding volume that also to be considered here for the calculation of height of the liquid in tray K. So, this height of the liquid in tray K actually as a function of that minimum tray spacing and corresponding volume of the liquid and also diameter of the column. According to this Sirik and Gu, the values for this H and H mean respectively can be set to 3.0 and 0.61 meter. So, as per this equation number 7, after substitution of this that H mean and also H, then what should be the Wk, that also you can calculate. Now, substitution of all expressions into equation number 1, that is objective function, after some algebraic simplification that will give you this equation number 8, and this equation will give you then that total objective function based on that different that cost function and also cost parameters, you can say. And after that you have to solve this problem, optimization problems, by algorithms. So, for that you have to assume some constraints there. In this case, as per Sirik and Gu 1994 for this reactive distillation column, and they have developed the reactive distillation column model based on these following assumptions, like the vapor and liquid phases are to be in equilibrium on each tray, that you have to consider. No reaction occurs in the vapor phase, that also to be considered. The liquid phase is always to be homogeneous, that is well mixed, and the enthalpy of the liquid streams is to be neglected, and also the enthalpy of the vaporization should be considered as constant. Both condenser and reboiler should be total, and also the temperature dependence of the reaction rates can be expressed in an that Arrhenius form. So, Arrhenius equations to be used for that the reaction, to calculate the reaction rate, and it should be temperature dependent. And column model, how actually that column model is developed, as per that Sirik and Gu, they have given the following equations from the material energy and stoichiometric balances, that is material balance over the bottom tray. They have given this F I 1 minus L 1 x I 1 to 1 minus beta plus L 2 x I 2 minus V 2 k I 1 to x I 1 plus summation of V I j j 1, that will be equals to 0, where I will equal to 1 to c. This is as per equation number 9. So, you have to consider this equation number 9 for your calculation. So, as per this material balance over the bottom tray, that you can consider this equation number 9. After that you have to do the material balance over the tray K. This equation number 10 is giving the material balance over the tray K, and what are the stoichiometric equations that can be actually obtained from this equation number 11 and 12 is given in the slide. So, summation of x I k, that should be equal to 1, and summation of k I k into x I k should be equal to 1. So, from this 11 and 12 equation number, you can calculate what should be the stoichiometric coefficients there. And in this case, some notations are also given as per equation 10, 11, 12. So, those notations to be actually considered for this particular equations for as the understanding of the different stream functions and other whatever parameters are to be there. And then you have to do the energy balance over the tray K, that equation 13 is giving this energy balance equation, and material balance over the reboiler, what should be that equation 14 is the material balance over the reboiler, whereas this overall balance of the component I can be expressed by this equation number here, if we consider it as 15, equation number 15. So, this equation number 15 will give you the overall balance of component I. So, we are getting that material balance over tray K, energy balance over tray K, material balance over the reboiler, what should be the overall balance of component I. And then you have to consider that distillate molar flow. So, in that case, this distillate molar flow DIST, it will be denoted by that. So, is calculated from the difference between the vapor flow of the top tray, that is Vn, and the liquid flow onto it, that is denoted by Ln plus 1. That is as per equation number 16, then you can calculate the distillate molar flow, that will be equal to Vn, that is vapor flow, and also that minus Ln plus 1, that is liquid flow. So, for total condenser you can consider that x I n plus 1, that should be equal to x into d I, and also x d I should be equal to k I n into x I n. So, according to this equation number 17 and 18, you can calculate what should be the mole fractions in tray n plus 1 and also n. And if you are considering the bottom flow rate, the molar flow rate of the bottom denoted by V 0 can be calculated by this beta into L, where beta is called boil-up fraction of liquid stream L 1, that is vaporized in the reboiler. So, beta should be equal to V 0 by L 1, that is given in equation number 19 in the slide. Now, after that you have to consider the kinetic and thermodynamic relationships, the extent of reactions J K, and the vapor liquid partition coefficients, that is K I K should be considered, and those can be computed for component I on each tray by this equation like this 20 and also equation 21, where this here W k this and T k are the liquid hold up and the temperature of the tray at K. And this reboiler and condenser duties, how to calculate that? It can be calculated from this equation number 22 and 23. That is Q b is equal to beta lambda into L 1 and Q c is equal to lambda into V 1 V n, and then Q b is computed as the energy required to vaporize a fraction B of the liquid of the bottom tray, and Q c is computed as the energy that is required to completely condensate the vapor flow rate of the top tray. And then how to calculate that column diameter? The column design that will be required for the evaluation of the diameter d, which is computed or calculated for the conditions at the bottom of the column from the following that is that equation that is denoted by equation number 24 that is given by Douglas in 1988, or you can follow that Sirik and Gu 1994 paper. So, where in this case the C d is a constant which is actually evaluated by knowing the molecular weight of the gas and the bubble point of the gas and the column pressure. So, it has the value of that 0.01331 as a dimensionless as per that Sirik and Gu that is given in 1994. Now, after that you have to evaluate the objective function. Now, the objective function, that is actually minimization of the total annualized cost, which is composed of two basic terms. This is called annual operating cost and the annualized investment. The annual operating cost actually it will come based on that raw material, steam and cooling water that is set for the operation annually, and it will be considered that annual operating cost. And then annualized investment should be the cost of the column shell, trays, reboiler, condenser, that will correspond to the annualized investment. And to evaluate this objective function, the operating conditions that will be determined by the column simulation for each decision vector that have to be that known for that evaluation. Now, in this case, what are the constraints? The constraints are that V k less than equals to F max. Here in the slides, all those constraints are given. L k should be less than equals to F max, and summation of F I k should be less than equals to F max, and W k should be less than equal to W max, and the maximum number of trays should be N max. So, in this case, you have to remember that this problem is a large, highly nonlinear, non-convex problem, function of N max. Since the material balances contain that bi and tri linear terms and the reaction terms, in this case the vapor liquid equilibrium evaluation and also the objective functions, all those that are highly nonlinear. So, it will be very complex and that to get that convergence, or you can say it will be very highly non-convex problem for your analysis. And in this case, what are the variables for the optimization problem to be considered? In this case, there are there are 3 n max plus 1 decision variables. One is integer corresponding to the maximum number of trays n max, and 3 times of maximum number of trays should be decision variables that will also be continuous, like the Boyle R fraction beta, the n max feed flow rates that will correspond to one of the feed, and n max minus 1 feed flow rates corresponds to the other component. And in this case, that the feed flow rate into the first first tray next to the reboiler to be considered here, and also n max liquid hold ups to be considered there. So, for the simulation of the column with n max trays, all the 3 times, that is 3 n max continuous variables are required. However, in this case, for a column with n trays where n is less than n max, only 3 n continuous variables are involved, while the other 3 into n max minus n are simply ignored in this case. And in this case, the simulation purpose, you have to use that simulation of reactive distillation process, which will involve the simultaneous solution of material and energy balances and stoichiometric relationships. This corresponds to the solution of a considerable large set of nonlinear equations. And for the calculation procedures that you have to that consider these categories given in the slides, like methods using equation for decomposition or tiering or partitioning, relaxation techniques, methods incorporating Newton or quasi Newton algorithms, homotopy continuation methods like this. So, you can follow this Lee and Dudukovic that is published in Computers and Chemical Engineering volume 3. So, you can have the idea how to calculate that that calculation procedure is there, in details it is given there. Now, there are several methods are actually decomposition methods, relaxation techniques, Newton or quasi Newton methods, homotopy continuation methods there. Now, decomposition methods actually it will allow the identification of blocks which need the simultaneous solution and blocks which can be solved sequentially. Relaxation techniques, in this case liquid phase compositions are to be computed based on non-steady state material balances, and which in subsequent iterations proceed towards the steady state solution there. Newton or quasi Newton methods in this case converge quickly for suitable starting gauges, and in case of homotopy continuation methods, the methods have the advantage of forcing the desired solution by tracking a homotopy curve regardless of the choice of the initial estimates. So, among these that various methods, relaxation technique is relatively more suitable to use for the calculation. Now, general structure of that simulation problem, a simulation model can be proposed based on the following steps, like this that an initial estimate of the molar feed flow rate not specified by the decision vector, like a torn, recycle or variable is specified there. An initial estimate of the composition profile in the column to be next to be obtained, and then this estimate can be improved by a relaxation method. The material balance equations then to be solved with the Newton-Raphson method, and then new composition profile is to be calculated, and the torn variables is to be reevaluated, and the equations that describing the reactive distillation process are again to be solved there, and the algorithms which will be ends up when the global material balance to the column is to be verified after convergence on the torn variable, and also or when a non plausible column is obtained there. So, these are the solution algorithms are given in the slides. Please go through these slide one by one. This that solution algorithm is given there. I think you can follow for this solution method how to actually that systematic way that problem can be solved. And in this case initiation is the very important one, that how to initiate that gauge of the torn. In that case it can be that large enough, but at least 50% larger to accommodate the desired production rate. That will consider that conversion which is not complete there. For the subsequent steps of the simulation, you can gauge the initial composition profile generally based on the feed composition, considering the same liquid composition all over the column there. Like as per Bestos in 1987, you can use this equation number 25 for this initial composition gauge. Now, algorithm for the initialization, in that case the algorithm for the initialization of the composition profile can be developed taking into account the two reactions and the specified product flow rates. Typically, from the stoichiometry of the reactions, the following reactions can be obtained, that is in equation number 26 and 27, and the composition in the tray next to the reboiler and the global extent of the reactions can be computed with the estimates of the product flow rates like P1, P4 like this here. And assumptions for initial composition of profile estimation here, in this case the extent of reactions, that is R1 and R2, that has been given in earlier slides, that is should be is the same in all trays with liquid hold up and null in all the other trays in that case. And the starting gauge for the composition of the liquid phase on the last tray N is to be 95% of the component 2 and 5% of the component 3. And the composition of that component 1 on tray N is re-evaluated if the liquid hold up for the reaction exists, and for each one of the other trays with the estimated composition of the top and bottom trays, this composition of the components 2 to 4 are computed using that linear interpolation and the composition of the component 1 which is set null for all trays there. So, with the starting gauge for the composition profile, the temperature profile can be computed there, and the temperature on each tray can be computed with the corresponding stoichiometric vapor phase. The solution of this equation can be obtained with the Newton-Raphson method, and also liquid and vapor molar flow rates also of the tray can be calculated with the reboiler material balance for the species that will correspond to the specified product. Now, so what is this actually Newton-Raphson methods? The Newton-Raphson method is used to compute that composition profile by solving the material balance. The application of this method is based on the algorithm proposed by that Bestos in 1987, but considering that the chemical reaction may be distributed over the several column trays, and with non-ideal vapor liquid equilibrium, it can also be considered that the reaction may be circumscribed to a single tray. Whereas, in the relaxation method it can be used for the requirements where a suitable starting gauge for the composition profile is required, and also the initial starting gauge for the composition profile is also subsequently to be improved by the application of a relaxation method during a pre-specified number of that iterations. Now, the convergence criteria also to be considered there, that during that simulation that with a feasible distillation column, when the global material balance of all components should be obeyed, that simulation ends up, and if convergence on the recycle variable generally obtained without convergence on the global material balance, in that case what you have to do, the distillation column is not a feasible one, and in that case the global material balance is assumed to be verified when this equation number 28 to be that satisfied. The convergence of the recycle variable are F is verified when this here it is given in the slides, this one. So, this equation number 28 to be verified for the global material balance for the convergence criteria. So, I think I should stop here, because there are several also materials also for the consideration of this optimal solution. So, I have given that basics of that optimization techniques by the simulated annealing for this reactive distillation systems. What are the different criteria, what are the different objective functions, what are the that assumptions to be considered there. So, I think you have some idea which may be helpful for further understanding of that optimization problem for this chemical engineering process intensification. I would suggest you to go further these textbooks, even some other that research papers that I have cited here in the slides also for your further understanding. So, thank you.